Video, we're going to review chapters 14 and 15, starting with the properties of acids and bases, which you should memorize. Both acids and bases will conduct electricity. The stronger the acid or base, the more conductive they are. They both change litmus paper's color, although differently. Acids taste sour while bases often taste bitter. Bases have a slippery feeling. Acids can corrode metals, and acids and bases will neutralize one another. There are 7 strong acids, strong meaning they ionize 100% in solution. Here they are, memorize them. Strong bases are the hydroxides. There are 3 main definitions of acids and bases. The first is Arrhenius. According to the Arrhenius definition, acids have an acidic H+, and bases have a basic OH- that's liberated when dissolved in water. The Bronsted-Lowry definition is a bit broader. Although acids are H+ donors, it expands on the definition of a base to include anything that's capable of accepting an H+. For example, NH3. The Bronsted-Lowry definition introduces equilibrium, wherein the acid on one side, having lost an H+, becomes basic on the other side, hence the label conjugate base, and the base on one side, having picked up an H+, becomes a conjugate acid. If there's a strong acid or base on one side, the system will not have an equilibrium, and instead will go 100% pointing away from whatever was strong. Acid-base reactions always favor the side with weaker acid and base. If acid, base, conjugate acid, and conjugate base are all weak, then there will be equilibrium arrows. This indicates that there is a significant amount of all 4 substances once equilibrium is established. Our final definition of acids and bases is the Lewis definition, wherein acids are defined as electron acceptors and bases are defined as electron donors. The Lewis definition expands on the concept of an acid because not only H+ is capable of receiving electrons. For example, BF3, where boron is lacking electrons, can behave as an acid according to the Lewis definition. This graphic portrays well the differences between the 3 definitions and how narrow the Arrhenius definition is versus how broad the Lewis definition is. On to some definitions. First, neutralization. When an acid and a strong base react, the products will always be some type of salt and water. Classic example being hydrochloric acid plus sodium hydroxide gives you water and table salt. Diprotic or polyprotic acids can lose 2 or poly meaning many H+. Examples include H2SO4 or H3PO4, sulfuric or phosphoric acids. Amphoteric substances are capable of behaving as an acid or a base. Water, when mixed with hydrochloric acid, behaves as a base because it accepts an H+. However, when water is mixed with ammonia, the water behaves as an acid, donating an H+. Also related to it being amphoteric, water autoionizes, according to this equation. The equilibrium expression for this equation is that Kw is equal to H3O+ times OH-, and at 25 degrees Celsius, that K is equal to 1.00 times 10 to the negative 14th. From Kw, H3O+ and OH- concentration, we can define pH as the negative log of the concentration of H3O+, and pOH as the negative log of the concentration of hydroxide. You may have previously learned that the pH scale is 0 to 14, but it is absolutely not. It can range from a little bit past -1 until about 15. By the definition of acidity, if you have more H3O+ than OH-, you have an acid. If you have more hydroxide than hydronium, you have a base. And since the product of the concentrations of hydroxide and hydronium will always be 10 to the negative 14th, that means that if your pH is less than 7, you have more H3O+ than hydroxide. And if the pH is greater than 7, it means you have less hydronium than hydroxide. For pOH, it's the same but in reverse. If you need to do calculations with hydronium concentration, hydroxide concentration, pH, and pOH, you should know that for strong acids, the concentration of the acid that you're given is equal to the concentration of H3O+. A 1 molar solution of HCl, a strong acid, has a 1 molar solution of H3O+. For hydroxides, you need to be careful with the subscripts. For example, if you have a 1 molar solution of magnesium hydroxide, because there's 2 OH-, your concentration of hydroxide will actually be 2 molar. To interconvert among these 4 values, you need to use this chart. I have another video in which I solve some practice problems using it. Weak acids and bases are a bit more complicated. Since they don't ionize entirely, you need to use a Ka for any weak acid or a Kb for any weak base. Generic forms from the chemical equations are given here and here, and the Ka and Kb are written accordingly. For any Ka problem, you'll need to use an ice table to find the concentration of H3O+ and A- at equilibrium. Since by definition weak acids ionize very little, we can say that the change in concentration of Ha is very small relative to the initial concentration of HA, and that can simplify our calculations. Always, if you're solving for the pH of a weak acid, which requires you solving for X in this equation, you will have Ka is equal to X squared over the initial concentration of HA. Weak base problems are solved rather similarly. Further, on the topic of Ka and Kb, for any conjugate acid-base pair, the Ka of the acid and the Kb of the base, when multiplied together, give you Kw. For example, HF has a Ka of 3.5 times 10 to the negative fourth. The Kb of HF's conjugate base, F minus, is equal to 2.9 times 10 to the negative 11th, and the product of those two is 1.00 times 10 to the negative 14th, Kw. What this means is that the stronger the acid, the weaker the conjugate base, and the stronger the base, the weaker the conjugate acid. HCl is an extremely strong acid, and so its conjugate base, chloride, is extremely weak. That's the reason why this is a one-way arrow and not an equilibrium. On to titrations. If you have an unknown titrand or analyte and add some drops of indicator, you can determine the concentration of the analyte by adding titrant of a known concentration and doing some stoichiometric calculations. By definition, the equivalence point in a titration is the point at which the moles of H3O plus and the moles of OH minus are equal. So you can solve titration problems using molarity of H3O plus times volume of H3O plus is equal to molarity of OH minus times volume of OH minus. Bear in mind, if you have a polyprotic acid or a hydroxide that has more than one OH minus, you may need to use a coefficient. For example, if you have a 1 molar solution of MgOH2, you will need to plug in 2 molar for your concentration of hydroxide, since the base has 2 hydroxides in it. At the equivalence point, a solution may have an acidic, basic, or neutral pH. For a strong acid and strong base, you'll have a neutral equivalence point. For a strong acid with a weak base, the products will be a weak acid, and the conjugate base will essentially be non-basic since it's the conjugate base of a strong acid and really doesn't allow the reaction to go backwards. As a result, the equivalence point will be at an acidic pH. The reason being that the conjugate acid, being a weak acid, is capable of reacting with more water that's available and forming H3O+. For a weak acid reacting with a strong base, there will be a basic equivalence point because the conjugate base of a weak acid, for example F-, is basic, and the conjugate acid, being water, is not going to make our water more acidic. Because you have a non-acid and a weak base, the overall net basicity will result in some of this fluoride reacting with water to form hydroxide and raise the pH. Because an equivalence point can be reached at acidic, basic, or neutral pHs, you have to take care in determining which indicator to use for any titration. For a titration that has a basic pH at the equivalence point, phenolphthalein is very useful, but for a titration that has an acidic equivalence point, methyl red, for example, might be more useful. And that's all for this video. I hope it's been helpful. Feel free to leave any questions or comments in the comment section below, and thanks for watching.